All right. Hello, and it's too loud, isn't it? Yeah. Wait. Okay. Hello, and welcome to lecture 4 of computer vision. So we are going to talk about image segmentation tonight, which is very interesting in computer vision. One of the main branches in computer vision is classification. The other one is image segmentation, and there are a lot of techniques for that. We are going to touch on the basis of image segmentation to see what it means, how it works, and in the next lectures we will look at classification as well. So what we will talk about is image segmentation using traditional computer vision. We are not in deep learning image segmentation yet. We will talk about this later. So the ideas for image segmentation are very similar to what we have had so far. We are going to see how we can use color intensity values, or we can use edges and so on to segment images, and generally what segmentation means. So before getting there, just a quick recap from last time. We talked about image filtering. We saw how we can do convolution on images, how we can have a mask and run it all over the image to extract edges, borders, corners, and so on. We talked about blurring, sharpening, and you did a little bit of Instagramming. You learned how to write your own filters, making your images look weird. So we are, one of the things that was mentioned in last lecture was about this face detector. Some of you had some questions about how it works, so I'm just going to have a few slides about that and a few slides on optical character recognition, how to find those numbers that some of you are now enjoying working with. So the face detector in MATLAB gives you a B-box, a bounding box. The bounding box is something which has x, y, width, and height. So once you have these values, x and y is the top left corner, and then you have the width and height. So what you need to do to calculate the bottom right corner is just a simple addition. So b box 1 is a, b box I and 2 is b, and c is a plus b box I and 3, and d is b plus b box I and 4. So this is very simple, right? Once you have the corner coordinates and you have the height and width, you just add the height and width to those values to get the bottom right. And in image processing, what you need to do is you need to have the top left and bottom right coordinates. Now you have the whole box. So you know where it starts, x and y, where it ends, x and y. So now you have the coordinates. You have a box, which is the bounding box of the object that you have in mind. In this case, it's a face detector. So let's say the task is to make, run your face detector on an image, and now you want to blur the faces. So how can we do it? There are two ways to do it. One is to detect all of those faces. So this is an old way of calling face detector as well, so I just put it the old way. There is a step function which goes through this. And then I find all of the bounding boxes, and then I say for I from 1 to n, for each bounding box, find the A, B, C, D, and then you extract that area. F is that area from B to D to A to C, all channels. And what I do is I apply a kernel, blurring kernel in this case. Create a kernel, apply it, and then put it back where I took it. So this is one way of blurring all the faces. So what you can do for your coursework, for example, for those who are going to deal with funny faces stuff, what you can do is you can extract each of those bounding boxes. So now you have them here as F, and then you can do whatever you need to do on that bounding box, and then put it back in the image. The other way to go around this is, instead of doing that extraction first and blurring each part, you blur the whole image, and then put it where those faces were. So those parts where we are going, so in this implementation, we just create one kernel. We just blur the image once and then put it back where we have taken those faces. So in this one, I create a mask, I create a kernel, mask or whatever, and then I find the locations and put that mask value from those locations into the image locations. So in previous implementation, if I had like 50 faces, I had to create 50 kernels and do 50 convolutions. But here I do one kernel, one convolution, and then put it back where I want. So this is, sometimes these small tricks in programming are going to make your code run times faster. So this is just to give you an idea. And for the number detection, some of you had this, a lot of trouble, I believe, trying to find those numbers. Numbers detection is not a very easy job. So don't underestimate it, but it's not that difficult neither. There are several ways around it. One, that I have put some code here. The way I do it is I do something called blob analysis. I find the blobs in the image. What is a blob? We will talk about it next week, but because some of you had the question, I just put it here. The blob is an area in an image that is like, it's uniform, it's outstanding, it's different from the background. So I use a blob detector, I extract those areas, and I have an estimate on the image sizes. I know if my image is, let's say, 1000 by 2000, that number area is something in the range of, let's say, 200 by 400. So I look for the blobs that are in that range, and I detect them, extract them, and then I send those to my optical character recognition. What is OCR function? In MATLAB, you have this link. Let me open it. So optical character recognition is a classifier, basically, that it looks at images and tries to find numbers and text in the images. There is a very, very good example here that, if I can find the mouse, where is it? Okay, so I think I quit this. Okay, so in this one, you see a very good example. The goal is to load an image, for example, a business card, and you run it through the function called OCR. Trust me, if you want to write this, is going to be a bit more than that. But now you have the OCR function in MATLAB. You just run it, and it detects the text for you. It says what this text is. Again, in this example, if you read through it, it's trying to find the numbers on this keypad. But it shows that it's a very, very challenging problem because the steps that it takes in the first steps, it makes a binary image. So technically, you lose all of the digits here. It doesn't detect anything. So it's showing you the techniques that they are going through to be able to finally detect numbers, but there are still issues. This is detected as a 1. We don't want that. So there is more and more. And you can read this example. It's a very interesting one. And it finally does the optic disc detection for you. There is another link here, which you can have a look again on MathWorks. It's automatically detect and recognize text in natural images. So numbers are also text, right? So you have 0 to 9. That's it, 10 characters. So all you have to do is to detect these 10 characters. And for that, you can use some functions in MATLAB as well. So in this part of the example, they limit the vocabulary that they are looking for it. So let me see which, yeah, here. So you constrain your OCR to say only look for these characters. So in this line, they are just limiting the number of classes that the function has to return instead of detecting all weird characters and alphabet. It's just detecting and returning numbers. So here you have another example. You can use, this one is using MSER features. We will briefly talk about them in lecture 6, but you generally have an idea what features are. So you can go through this example as well and see how they are detecting characters in natural images. Similar technology is used for detecting license plate numbers once a car needs a ticket. So this is just an idea of how you can kickstart with your OCR bit. The other way to go around it is you can try to train your own network. So you have a network that is trained on detecting numbers. You train it, you give it a lot of input numbers. Those numbers are labeled, you know the output, and your network learns. We will talk about supervised learning as well. You will, if you don't know what I'm talking about, you will know soon. Not tonight. So what we do is we train a network, we feed it a lot of input images, and the output is the label of that class. And then what we need is an object detector. So our object detector goes around the image, looks at different areas in the image, and once it detects a part that sounds like it could be a number, then it sends it to the classifier. So for that, in deep learning, we have CNN, which is classifier, and then we have RCNN. It's different with RNN. We have CNN and we have RCNN, regions with convolutional neural networks. Then we have fast RCNN, faster RCNN, mask RCNN, and YOLO. So these are the methods that are used in deep learning for object detection. For classification, it's CNN. So the way we do it in traditional computer vision, as I mentioned, is you can detect features from images. And all of those deep learning models also are extracting features, but the way those features are extracted are different. In traditional computer vision, we extract features like corners, edges. We tell the network or our model what our features are. In deep learning models, the model extracts the features itself from training images. And from like looking at millions of images, it learns those features. So previously we had masks, like 1, 0, 0, 0, 1, 1, you remember? So they were the kernels that we hard-coded. But in deep learning, we start with random numbers, and the network keeps training and updating those weights until it finds the optimum weights. So if you want to detect, for example, circles, where one of the questions was, deep learning can extract features that are more complex. They don't only extract edges or corners, they extract circles, they extract color information. So those features are learned. But in this case, we extract those features. Blob analysis uses some techniques like saliency maps, finds things that are outstandingly different from their neighboring areas. Anyway, so this is my way of detecting that number. So the image you see here, I'm drawing a 1. So this text here says 0, 1. So I'm finding that area and drawing a box around it and saying 0, 1. I put the code here for you. It may work on your images, may not. You can try to see how it works for you, and you see which parameters you need to change. But what I am doing is I'm detecting the region of interests where I think there might be something. And depending on the image size, I'm saying if the region of interest size is bigger than 150 pixels, because it finds a lot of tiny areas, which I know it's not my number. My number is a bigger one. So I eliminate that, and for those, I find those rectangles, and then I run OCR on it. Another important thing in computer vision is image resolution. If OCR is trained on detecting numbers that are usually, say, 50 pixels by 20 pixels, for example, and then you are feeding an image which is 500 pixel by 800 pixel, your model will not be able to capture that variance in a scale unless it has specifically been trained. You remember the example we had for detecting the nose? And it was detecting an area which, to our eyes, it doesn't look like a nose. It's just like a white column and like two darker areas around it. But the computer doesn't know. So it just looks at the images that it's trained on. So always compare apples with apples. If your images are low resolution and you have an input image which is of high resolution, you have to think wisely how you can run this image. If you just run it over a low resolution trained model, it won't work. And then I'm showing those images as a montage next to each other. Anyway, so these are just some quick answers to some questions you had. During the labs, I'm always happy to answer any questions that you have regarding coursework and tutorials. So, overview of today's lecture. We are going to talk about image segmentation, as I said. So, first thing is we are going to define what image segmentation is. Then we will start from thresholding, how we can basically threshold an image. We just put a number and say if something is bigger than, say, 50, it's background. If it's lower than 50, it's foreground. Something like that, as simple as that. Then we have clustering, watershed, active contours, graph cuts, and then we will see how we can see how good our model is. We have produced some results. Now we want to see how good are we, how we can compare this model with that model. So segmentation is basically a task of partitioning an image into different groups. Classification is that I give you an image and I say, what is it? Is it a cat or a dog? Then you have to classify it, right? Your model has seen a lot of cats with different backgrounds. Maybe some of them were in a forest, some of them were in a street. The background is there, but your model has to be able to capture it. If there is a cat in front of a car and there is a dog in front of a car, it has to be able to say which one is which. It shouldn't confuse them because of the background. So your model has to have seen enough images with different backgrounds to be able to extract those features. But segmentation is for individual pixels. So classification is for the whole image, but segmentation is for individual pixels. For individual pixels in this image, I'm going to say which ones are the foreground, in this case my eagle, and which one is the background, like whatever, ocean. So what I need is a method to find foreground and separate it from background. It is very easy for us. If I show you the image on the left, what do you see? A smartphone, right? Nobody would say, I see there is a sunset and on top of an ocean. You see, you don't see those colors because you're looking at it as a whole. You see it's a mobile phone, right? But in this one, it's a bit trickier, but you still can see the dog. The Dalmatian dog is the head. See? You see the dog. It's very, very difficult and impossible for a computer program to detect this dog, but you can do it. So for our brain is very, very simple, but for computers is not. So segmentation has a variety of practical uses. You can do cutout, you can do recoloring, which Sam did for the last lab. You can do compositing. One of the interesting uses of image segmentation is you can write a program that detects all the green, which is a color we don't usually see in normal scenes, or all the blue, whichever you like, and replace it with something. Does it sound familiar? Let's watch this video. Game of Thrones is coming in 2 months, so I thought you might like to see that. Let's see how it's made. The spoiler alert is that you're not going to be able to do that tonight, but the general idea is they are using a lot of visual effects, but the main idea is they have a green screen or a blue screen, which usually people don't wear. We will look into it later as well. But what happens is they do a segmentation, they find the green pixels in that image and replace it with whatever is the background that they have made. So that's another kind of segmentation, just simply put. In the lab, you will do a Superman imposing on a London skyline. So you have an image, the Superman in front of a green screen. He's not doing anything, but you just detect the green color in the background, replace it with another scene. So again, it's the same idea. You remember for the bounding boxes for the face, you find the bounding boxes, and then you replace that blurred image into them. So here you find the ones that are green, and then you superimpose something in those pixels. So we have seen how interesting segmentation can be. It can be used in medical images as well. For example, you can detect the bounding areas of different vertebrae and find a standard shape, how a normal one would look like. And then you say, okay, if this is a normal one, then if I have a new image which doesn't look like this, then this is probably a pathology, and then you inform the doctor to look at that particular point or whatever structure you're looking at. It can be used in brain images. You have MRIs, for example, and you can color it, say which area is white matter, gray matter, non-brain, and CSF. But as you can see, it can be segmenting into two classes, or it can be more than two classes, depending on the task that you have. And it can be done on two-dimensional images or three-dimensional images, videos as well, so, or 3D images, whatever format that you have. It can also be, for example, run on a video, and well, this is detecting a dog skateboarding. Okay. Under and over segmentation is when you have an image and you're segmenting it into too many segments, you are over segmenting it. It's very simple. And if you are not giving enough segments, you are under segmenting it. So with under segmentation, you are actually losing a lot of information. With over segmentation, you are not gaining much information. Let's count the birds in this image. I want to count the number of birds in this image. What should I do? The first step is, as intuitively, birds are darker than the background. I have to find the darker areas, right? So this is the first step. Let's find the dark blobs. So we first load the image and convert it to grayscale. Can do I is RGB to gray, imreadbirds.png. This is my bird's image. It gives me this image. Just you can resize it as well, but it doesn't have to be. The idea of thresholding is very simple. It's a very, very simple binary classification. What I'm saying is if the values are lower than the threshold, set them to black or white, depending on what I like. And if they are higher than a threshold, set them to the other color. So I'm making the image binary. So in this case, I'm making my birds white. So if something is lower than, let's say, so the values are between 0 to 255. So I just decide, let's do, I don't know, 120. Let's see how it works. And then I do, let's put the threshold at 65. Let's do it at 180. I manually decide what threshold I need. So this is my image at threshold 30. So if I say, if anything is under 30, set it. And by this one, this equation in MATLAB is very, very simple. It automatically generates a binary image of size I and puts whatever is in it under 30 as 1 and the other way around as 0. So here I get my image. So as you can see, if anything is under 30, I am losing this bird, right? because this is a bit brighter. If you look at it, there is some cloud around, so this is a bit brighter. So I am losing that bird here. So let's make it a bit higher. Let's say 70. I see some of the branches here, which is not what I want. They are not the birds. And if I set it at 120, then I see way too much. I don't want that. So probably something around 70 would be good, because I don't lose this one, but I still get these branches. So now I have to find a better one. But before doing that, let's try the value 70, which seemed to be a good one. Didn't miss any birds, and it has just some branches. So I get my image, and I create a binary image by thresholding the values that are under 70. I'm show the image. So this is the first one. Then I am open. What does it mean? We will talk about it. But what this does is it gets rid of branches. I will tell you why this happens in the next few slides. But what it does, it cleans up my segmentation, makes it like this. And then BW label is another function in MATLAB that counts areas that are connected. So this area is connected, right? The pixels in it, in a neighborhood, they are connected. They all have the same value. They all are 1. So it detects these and gives them a number, like 1, 2, 3, 4, 5, 6, 7, and so on. And then what I do is I use image SC and then give it a color map. So each of those labels is now a different color, and it just paints it for me in different colors. And it tells me I found 12 blobs or areas that are connected. So I have counted my images. So BW label labels n connected components. What does it mean? We will understand. And IM open is a morphological open operation, which is an erosion followed by dilation. Okay, too many technical terms. Let's look into them to see what they mean. So mathematical morphology is a related class of nonlinear image processing techniques, which they also use kernels. They are basically mean and max. So they look at a neighborhood. In deep learning, we will also do max pooling. Not that often also do mean pooling. So if I have a 3 by 3 area, I look at it and I pick the maximum value. This is called the max operator, as simple as that. If I have a 3 by 3 area, I look at it and pick the mean value, the minimum value. So that's a mean filtering, or pooling, they call it. So in deep learning, we will also see that. That's a very simple operation. So erosion is a mean filter. Dilation is a max filter. A closing is a dilation followed by erosion. So if I do this in an area, I'm taking the maximum and then taking the minimum. Doing this fills holes smaller than my filter. You can define how big a neighborhood to look at. 3 by 3, 4 by 4, 5 by 5, 1 by 3. In this example MATLAB has, you can see more details about it, how the kernels look like. But they are basically just max and mean. We don't do anything. An opening is erosion followed by dilation, or let's call it mean max. So you first take the mean and then take the max. And what it does, it removes objects smaller than the structuring element, which is our filter. It can be used for cleaning up segmentation. Let's look at an example and see what it means. So I have the original image. Eroding, for every area it picks the mean value. So you see the black is picked. I see the mean value. But when I have a white area here, if I look at the neighborhood around it, the minimum value is always the black, so it picks black. So I'm losing the tail here. But I'm making this line inside a bit bigger. The same goes here. I'm losing the tail, but I'm keeping the image inside a bit bigger because I'm doing a mean max. It's a mean. And here I'm doing a max. So for every area, it's just detecting the maximum in its neighborhood. So here I have zeros, and then I have ones, and for every area it's taking the max. 1 is bigger than 0, so it's filling it. So as you can see, eroding makes the tails gone, dilating makes the face gone, which is inside, right? So it's filling it. And you can do closing and opening. So if I want to get rid of both outside and inside, I close the image and I open it, or I open and close it. So I'm cleaning it. I'm eliminating the areas inside that I don't want. It's very simple. There are other ways, there are other functions in MATLAB that you can use for cleaning up your segmentation. You can use IMFill. It fills an area. So if I have this image, there is a bounding box around this area. It finds that bounding box, the connected areas, and then IMFill fills it. It becomes like this. Or I can use, it's not BVAR field, it's BW area field. So you can use this one. And what it does, it's, you can say which size of connectedness in pixels you want. So in this case, I say, I just want areas that are connected and have a size between 40 and 50 pixels in this image. So if I give this image as an input, it gives me only the T and R. For example, the capital T, the S, A, they have more connected pixels than 40. So it's not picking them. So it looks for connectivity. And it's very simple. It just goes around in a neighborhood and sees how many of those pixels are connected. But what we are talking about is connectivity. What does it mean? We need to define a neighborhood. What does a neighborhood mean? So if I have a pixel, I can just define areas around it. As you can see in that image, I have four neighborhood, 9 neighborhood. It's just a very simple idea. You have, like in one part of your image, you have whatever number. So let's say I want to look at this area. A max filter returns 17. A mean filter returns 5. Connectivity means if I have this pixel, I see if it is a 1 in value, pixel, this is, let's say it's a 1, and everything else is 0. It looks for the ones around it, depending on how many I want. If I want a 4 neighborhood, I look at these 4. If I want bigger neighborhoods, I look at all of them, 9. If I have 3D images, I will even have more possibilities. Right? So this is the definition of neighborhood. So now we are adding a spatial information as well. It's not only the brightness values. So now the challenge is finding that good threshold. As you remember, what we did manually, selected 70 and did some cleaning, like opening, closing stuff, and made it clear. But that number, we chose it manually. We tried 30, 70, 120, and we decided 70 is better. Now we want to choose it. We want a program to choose it for us. How do we do that? One way is to look at the histogram of the image. You remember we did that before for that car image, and then we stretched the histogram and made it look a bit more beautiful. So here I have an image, and once I calculate the histogram, IMHist, I will see something like this. So it's telling me that some of the values are in the range of 0, which is probably this area, which a doctor would say is probably air. I don't know. We have this color, and then we have this color. So is this a good threshold here, 150? So if I do that, I get something like this as a binary output. It's pretty good if I want a binary image. So one way would be to find that point in my images. One of the ways that people used to publish papers was finding the good threshold. So for example, for skin tone detection, there are a lot of papers to say which ranges of color are of a skin. So they look at different data sets, but this bit is important to see what data sets you're looking at. If you're looking at, say, South Asian data sets, if you're looking at Caucasian data set or black data set or Chinese maybe, different races, they may have different skin tones. So this one is where you need to be careful with the input. So you cannot generalize. If a data set is working very good on, say, black people, it might not really work good on white people. So what they are doing in this case, they are not looking for shapes for difference, like you remember we did like eyebrows and eyes. Here they are looking for only color tones. So in one paper, they convert the images to YUV, which is another color space, similar to HSV that we had before. It has 3 channels of Y and UV. Now there is more detail about it if you're interested. So they are converting the images to YUV. The code in MATLAB is RGB to YCB CR. And once the images are converted, they define a range. They extract the color channels, and then they define a range and say find whatever that has a U over 77 and under 127 and so on, and for V over 133 and under 173, and they calculate the final image. It's a binary classification. So it's just basically like RGB channels. We say if R is between 0 to 80, for example, this is probably not really red image. You can just say that part is, it could be face, something like that. Different people have proposed different models, different ranges for a skin tone. So if you look at like Altairi et al. Or Chai et al., you can see different equations they have provided. And you can run them on images to see which ones look better. So these are original images, and this is the skin tone detection of Chai and Tairi. So this one is detecting the whole area as a face, but this one is not detecting as a skin. This one is not detecting the eyes and mouth as a skin, which this seems to be better, right? Because eyes, the eye color and the mouth color is not a skin color. It's not what we assume as a skin. But be careful with what you're wearing. So sometimes if you're using a skin tone, you can use a skin tone in your code to detect faces as well. So you can run those 2 equations and see how faces are detected. But in your case, be careful, because these benches are probably going to be skin tone. But we didn't take the photos here, we took it in another. So it may be, it may not be. You can try. That's another way of detecting faces. You can use a skin tone. So this looks familiar. So far, segmentation looks like a classification task. You define a rule, you say this is my threshold, this is the line. If anything is over that line, it's class 1, it's under that line, it's class 2, or the other way around, right? So segmentation is sort of a classification task. This is a rule-based classifier, and we need to find the threshold. So far, the human has done it, we decided. But now we are trying to find a better threshold automatically. So we can do the histogram, and as we saw before, we can calculate a number like that. Now we are looking for automatic thresholding methods, how we can do that automatically. So many of these methods try to determine a bimodal histogram. They believe this is something we have. This might be the background tones. This is probably the foreground tones. So there should be a line here or here, and they try to detect that line where exactly is the best point to separate background and foreground. Otsu, one of the first to propose this model, is using a very, very simple model. It's trying to minimize the intra-class variance. What it means is if I have foreground pixels and I have background pixels, I know which ones are foreground and which ones are background. I'm trying to find the threshold that limits the differences between each class values. So finding that value is what it's trying to do. If you remember previously, we could look at the histogram of an image as a PDF, probability density function. And the goal here is to find the value that separates these two classes based on that PDF. It's a very, very simple way to do it. We set t to some initial random value and determine foreground and background pixels. Then we compute MB, the mean of the background, and then the mean of the foreground based on the current value of t. So I just start, let's say, 70. I find the mean of the ones that are lower than 70, and I find the mean of the ones that are higher than 70. So far I have the mean. And I keep doing that. I change that value based on the means that I am calculating. And I keep doing that until the differences are negligible. So let's see how it works. RGB to gray, I am read. I start with T50. And then I say last T was 0. I calculate the difference between T and last T. Yes, 50 minus 0 is greater than 1. So I put T in last T, and I calculate the mean of foreground as the ones that have a value over 50. And then I calculate the mean of background as the mean of the ones that have values lower than 50. And then I calculate the mean of these means. So 1 over 2 times mean of background plus mean of foreground. At some point, this will converge. In this example, in 5 iterations, I will start with the t at 50, and then it goes 81, 126, 138, 39, 39. So the changes are now negligible. So I realize that 139 is a good point here. So this is k-means. You remember k-means in unsupervised learning? So you start with random kernels. In this case, my classes were 2. So I only needed 1 threshold. Say whatever is over that, whatever is lower than that. I find 2 means for my classes and say the ones that are closer to those 2 will go next to that, will belong to that class. So in this case, k is 2. I'm finding 2 classes, foreground, background. So I'm sure you all know what k-means is, right? Yeah? Anyone who doesn't know what it is? Or dares to say doesn't know? No. Okay. So k-means is a very simple unsupervised learning algorithm. What we do is we basically randomly initialize means. I have this image of a lecture theater. I don't know how many classes I have. I say, let's say 5. I randomly initialize 5 values. 0, 60, 80, 90, 185. And then I calculate the values of the pixels and find the closest one to that number and keep updating that value that I initially created. Let's look at an example. So if I have this image here, I want to visually believe this is 2 classes, right? This is just my gut feeling. I think, yeah, 2 classes probably. So I randomly initialize 2 values. And I find the ones that are closer to this one. And say these are class 1. And mark them red, class 1. And the ones that are closer to this one, I say these are class 2. And mark them blue. So now I calculate the mean of all red ones. The mean comes here, right? Because there is more density here. And I calculate the mean of all the blue ones, and the means comes here. So now I calculate the mean of the ones that are closer to this blue mean, calculate the ones that are closer to this red mean, and then the mean comes here, and this one comes here. So these are now blue. And the last step, there is no significant change. So this is k-means. But there are a few problems with k-means. What is k? In that example, I could see there are 2 different groups, 2 different clusters, and I'm going to choose one. how to initialize the mean. You saw that I randomly chose these two, but if I choose, I have a higher modality image and I randomly choose that mean value, I may end up with different number of clusters. So how do I choose this value? And how do I calculate the distance? Here it was very simple. I said, yeah, they are the ones that are closer, visually I would say, but how do I do it in, like when I have a million dimensional data? Like, we don't really have million, but let's say 5,000 dimensional data. How do I deal with that? So there are some solutions, but we will look into them. We will look into them once we reach it in unsupervised learning. But what you need to know is one of the ways to calculate the distance between two pixels is their Euclidean distance, and the other one is a city block. So if I have a pixel here, let's say pixel 6, what is the distance with 5? It's 1. It's very simple, right? It's one spatial distance, one unit. And this is 1. What is the distance with this one? It's 1, something like that, right? So I will have 2, square root of 2, right? If I go with Euclidean distance or L2, this is called L2. So if you see this term, don't panic. It just means that. And if I do the L1, is that. So in L1, I'm just doing 1 plus 1. In L2, I'm saying a square root of 1 square plus 1 square. All right? So L2, in this case, between this pixel and this pixel, is the square root of 2, and with the L1 is 2. Again, for another pixel which is further away, you can do the same thing. So this is L2 distance is 2, L1 distance is also 2. But for this pixel, L2 distance is, right? And the other one is 3. So the reason we introduce L2 is because it's more accurate. It's the actual distance of two pixels with each other. But the reasons we have L1 is because it's simpler to calculate. If you are going to do 1,000,000 calculations for like any image, imagine you can save a lot of time using L1. You lose a bit of accuracy, but you will save a lot of time. Anyway, so these are some issues with k-means. We will address them once we talk about unsupervised learning in lecture 6. But now you have the general idea. If I know how many means I want, if I know how many clusters I have, how many groups I want, I can do that. So in MATLAB, there is a function called k-means. You can look at the details, but what it does, it needs an n by m matrix. It doesn't accept images as they are, because your images are n by m by z. Your images are, let's say, 600 by 500 by 3. But MATLAB, k-means wants m by n. So what do? I reshape, I flatten it, yes. Because here I don't care about the spatial information. So what I do is, instead of having an image which looks like this, I have an image which looks like this. I take one row here, next row, next row. So what I do is I reshape it. So in MATLAB, I have this function, reshape. So I reshape my image and then have those values. So now my image was 600 by 500 by 3. Now the new dimension is 30 by 3. So now I have the values. I pass it to k-means, and then it starts that iteration. I can give it more parameters to say what exactly I want. And I say 4 channels, 4 means. So it gets this input image and then converts it into this one. And you can use the color map GCA, gets current axis, and shows it on this one. So it color maps each each of them. It calculated the value of the mean, and it's just showing the value of the mean for that whole cluster. So this is one mean, this is one mean, and one mean. So here I have 4. So here is another exercise for those who are interested. We have randomly chosen these 2 numbers, right, as our means. We don't know where to select them. So another way is, instead of randomly selecting values, I can choose existing values as means. So here I choose 2 of the values as means, and then so the closest ones to this are these 2. So if I update the mean, I will have an X around here. And the closest one to this are these and these, so somewhere around here. Now I have new ones. The closest one to this are these, so the X will shift a bit here, and this one will shift a bit here, right? So I end up with something like this. So you can use some, I have put some script if you want to play with it later. You can try some k-means here as well. It's basically the same thing that we did in the last slide. As I mentioned, if I choose k, different numbers, I will have different classes. So here is k equals 2, k equals 3, 4, and 5. So it counts the majority of the pixels, finds the closest values. But here it's not considering a spatial similarity. It's only looking at brightness value, color value. You remember we just flattened the image, we reshaped it. So we don't have the spatial information anymore. We are not looking at the 3 by 3 neighborhood. We are looking at color values, trying to find the colors that are closer to that. So if you run this example, I ran it once with k equal to 4, and then I ran it again, and it gave me different outputs. So depending on the initial value of k that you select, it may generate different results. So one of the ways to deal with this is you can replicate it. You can get your k-means program to run 10 times, and then see which ones are more frequent, and then choose those.
You've reshaped your matrix. You lost the color information, as in, so something that would have been, say, mid-level blue and mid-level red. Now, doesn't that look the same when you're doing?
No, we still have that times 3 kept.
Oh, so you still have 3.
So we just did the row and column values. We just, as I said, so if the image looks like this, and I have 5, 5, 5, 6, 6, 6, 7, 7, 7, what I am doing is I'm making it like this. So the values are not changing. So if each pixel is 5, 3, 1 in 3 channels, I am still having it as 5, 3, 1.
So is it a matrix that's 3 times wider? Or?
It's making the matrix wider, yeah. It, instead of like a square matrix, you now have a row. It's one row. But here it was like 600 rows, 500 columns. But now you only have 300,000 values. You don't have a spatial information here anymore. So, now we saw how we can do it with a few means. Now we are going to look at thresholding again. Now I'm trying to find the threshold value, but this time hysteresis thresholding uses 2 thresholds. Okay? So the difference between thresholding and hysteresis thresholding is that you have 2 thresholds, and some people don't know it on the exam. So the question here is, we want to find a lower threshold and a higher threshold and see which ones are connected in the lower threshold area and have a higher threshold in them. Let me explain. I have this image and I want to find the bright blobs. If I do something like anything that is greater than the higher threshold, I see something like this. Let's say this is high threshold is 150, for example. And then I have a lower threshold, which is something like 60. So I'm saying if anything is higher than 150, you see it. If something is over 60 here, not Siri, you see it. So if something is over 160, you have it here. And if something is over 60, you have it here as well. So what I'm trying to do here is I'm finding connections and these ones. So how do I use these two sources of information? I read my image, I convert it to gray, so this is my image, and I show it. I define a value, a higher threshold as 150, and the lower threshold as 80. And say H, my high value images, is the ones that values in that image are higher than T high, and show it. So not this one, this one. And then I show the ones that are higher than T low. So you see both is higher. It's not lower than T low. Higher than T high, higher than T low. So this is higher than T high, this is higher than T low. And then I do something called BW label, which we used before. It labels connected components and find the ones that are unique in H and are a member of L. What does it mean? Is look at this one, and if an area, a unique area, so this is one unique area, 2, 3, 4, 5. If an area is here, now find the neighbors in this one. So what I am doing is I am showing so I don't want this one because this is not as bright as I want. This is not higher than my T high. But I don't want just this tiny point. I want the full blob. So I look for the ones that are connected, is member of the valid labels. So I have labels and I have valid labels. Labels are the ones that are taken from L, lower threshold, and I make sure that I'm choosing the ones that are also in H. They have a member in H, which means if a part of a blob is bright, I want to see the whole blob. I don't want to just see a tiny part that was bright. Okay? According to the faces, everyone understood. So, what we are doing here, we are taking the parts that are higher than a threshold, but keeping the shape of that actual blob. So here we have a hysteresis threshold. We can use it for edge detection, for example, to improve the images that we see, and we can make it more connected, like if there is an edge. So what this is basically doing, it says if there is an edge and some parts of it is less bright, make it brighter, keep it. But if it is not connected to this, and this area is not bright, then lose it. It's not significant. So if I have some information, if I have a corner, for example, in my image that looks like this, I'm trying to pretend that this is... So if I have something like this, and this area is very, very bright, and this area is a bit thinner, less bright, I want to keep the whole edge. I want to keep the whole corner. So this is what hysteresis thresholding does for us. Any questions? No? Okay. So, let's take a break and we will come back in a few minutes.
Spatial, why you lose spatial information.
What is it, Josh? Ask me if I know.
So the problem is that MATLAB likes that my input image or input vector, whatever I'm giving it, as a m by n format. So for me, n is 3 color channels, and now instead of feeding 600 by 500, now I shred my image into lines and put lines back, like the color channel. So now I have something that's like a bigger value, longer, but in one row. In this case it was a square, but here is row. So what I am losing, in this one, I know this 6 is under 5, but in this one the 6 is after 5.
Right, okay, so you change the connection. Is there a specific reason why it does that? Every type of form?
Because here, in this one,
Is that only in MATLAB? So my question is, what do you do?
when spatial information is not important and only color information is important, you have to, you don't need to have spatial information. But your question, it depends on what n is. N is important. You don't want to distort n, because if you lose the values of RGBs, then the colors are totally lost. Then you will lose color. Because k-means function is a function that is not only used for images and is used for all other sort of vectors, there is only one implementation in MATLAB. But in Python, there is a k-means for images, which you don't need to reshape your images.
For my coursework, to get access to GPU, I decided I want to do my work on AWS. And I've done some proof of concept there. The machine image is going to be Python and Keras and TensorFlow. But I don't know well enough yet to know that it's safe to commit to that. Can I do the coursework in a Python Keras environment? There's so much MATLAB stuff specific to MATLAB. Am I going to find counterparts of the MATLAB stuff?
There are all of these are implemented. Not in Keras, so when it comes to Keras is a platform for deep learning. These days, there are like open computer vision libraries that you can use them to Python, through C++. All of these functions are there.
Oh, so I might need to
All of these
install some additional stuff on my AMI.
But when it comes to AWS, you don't need this. What you need is Keras TensorFlow.
Thank you.
Because you use that for deep learning. For this one, you use it for computer vision, OpenCV. OpenCV is the equivalent of using all these functions in So all of these functions are here, but different meanings. So you use to learn different
So all these computer learning noise reduction and sharpness and all that, when you're doing like classification with square, for example, are you supposed to like have the images, do you like do these noise reduction techniques and then use that as the input, or do you expect the CNN to survive CNN?
There is something called pre-processing. So in your implementation, you can do pre-processing, like routing stuff, like noise removal, like improving your edges and things like that. It depends on your deep learning models. And algorithms also augment your models. So you do some augmentation on your data, you can vary noisy, add those distortions to your images so that they generalize better. So you can do pre-processing, but in most recent papers they show pre-processing doesn't really improve that much.
Yeah, that's what I'm saying, like, saying now, like, like, CNN should be able to, like, learn it. So, for example, an option would be, like, you have one image of
That's what they told me.
So that's
This is to generalize your model. So if I have only one image of your face this angle, my model is going to learn your face in this angle. But if I have these different colors, then my model learns to deal with different angles. It generalizes better. So that's all.
simple question. I'm sure it's going to coursework later, but I'm just wondering, what's the actual pipeline for site testing? For testing, so I understand generally it's a picture of my face and I'm number 7. So you keep a picture of my face and then it shows someone here, it shows a picture of the, is there one picture of the class or are you using each of your
I input the image, and I don't find the number. So it finds the number 7 in your image and shows you where it is. And it also draws this thing around your face and says person number 7. So it's basically
in terms of the actual you're giving it raw picture of an area of my original face.
it's one of those images that looks exactly like you. But maybe I don't have your face, maybe I have someone else's. So it's anyone. And there is a group photo, but you have to extract each face. And say this is face 7, this is face 9,
It should be adaptive to all, if there were 8 or so group pictures. It should be adaptive to any of those, or just remember you know the one is is it that picture or any of those?
it's not that.
Yeah, any of those.
You don't have that. One of those images that I have held, you don't have.
Okay.
And one of the images that you haven't seen. It's very similar to the image that we have. So we took 10 photos, I gave you 9, just 1.
But so it should be able to work on this.
It's very similar to the one.
Can I show you something?
Yeah, sure. Did you try this?
No. It's about K-means. During the first term, I developed an interactive application for K-means. Basically, it's interactive. Here you have the cost function, the inertia, or the distortion, and you can create sample size. You choose these are the number of clusters within the data, and these are the number of sanctuaries that you want to decay, basically. And then it can be played interactively, and then you have the expectation and maximization steps. And basically, this silhouette analysis gives you an idea about how good your cluster is. Basically, here you see these 3 are very bad, and you can see them here. I developed this application to show the shortcomings of K-means when it doesn't work. And as for the initialization problem, well, you can either do it randomly or use K-means ++.
For that, you can use elbow.
The elbow method to choose the number of K. That's a heuristic, yeah. There are other ways, other words, more robust. I haven't published it on my GitHub yet.
Very impressive. Good stuff.
All right. Okay. We don't have much time, and I only have 40 more slides left. So. Back to the previous discussion. I have about 35 slides, so I tried to make it a bit faster. But back to the previous discussion, we talked about spatial relationships that pixels have towards each other. They have like defined neighborhoods. We said 4 neighborhood, 8 neighborhood in 2D, and we talked about 6, 18, and 26 neighborhoods in 3D. So we can use that information, and one of the ways we can use it is in MATLAB there is a function called bwdist. So let's assume I have a matrix like this. Everything is 0 and I have a 1 here, and everything is 0 and I have a 1 here. So bwdist, what it does, it for any value that exists, like a 1, it finds the distance to its closest, to the closest seed. So the distance of 1 to 1 is 0. And now this guy's distance is 1, this one is 1, this one is 1, this one is 1.41, square root of 2, so this is the Euclidean distance. So this pixel is closer to this one, so the closest value is 1, this one is 2, this one is 1, and so on. So this one is 3.1. right? So what we are getting here is a distance, Euclidean distance map to the ones in our matrix. Is it simple? Bless you. And it also returns an index. It says, so this is value 1, 2, 3, 4, 5, 6, 7. So this is index 7. And this is index 19. So it says the closest one, this is closer to number 7. And these are closer to number 19. So BWDist automatically calculates the distances from existing values in our binary matrix. What can we do with this value? So if I have an example like this, I have these areas. Any segmentation model that I use is going to tell me this is one area, right? This is all connected and it is all ones, so this is one area. But visually we know that these are 3 circles that are overlapping. So if I want to find these 3 circles which have a line of contact, let's say, how would I do it? So the first step is I read my image, 3 circles, convert it to gray, and then convert it to logical. Logical means 0, 1. So it converts my image into zeros and ones. So I converted an image of 3 RGB values to only 1 bit per pixel. 24 bit, now it's 1 bit in just one line. And then I show my image, which is this one. Then I run the BWDist on it. So these are ones, so the distance is 0 to itself, remember? 1 to 1 is 0, right? So here these are all zeros. And the further it gets, the value is higher. So what I do is I get the negative of that image. So all of these zeros become 1. And the closer I go, the less, right? So I converted this to black and this to white. All right? So now I have converted my image into this. The next step is to set the ones that are, so what I do here is I get a negative of my D2, which is this one, and eliminate the values that are negative to minus infinity, which in this case is 0. So I convert that image to something like this. If I surf it, there's a function in MATLAB surf. It generates a surf for me. You see it looks like there are some cones, and you could consider it, let's say it starts raining. Once you exclude the background, the water will start to accumulate in the basins. So it starts to accumulate here, and it keeps coming up. So now we can look at each of these as an area in binary. As the water is continually added, these regions will collide, and they will have a ridge line. So the function watershed converts that image. It starts from an area, and once it reaches those rigid lines that are calculated from different basins, it stops. So you can try it with different images to see how it works. It has some applications. So I have an image like this. I find some seeds on that image. So in this one, I'm using IM regional mean, which means any region that has a low value. It just detects that region, a spatial neighborhood which has low value, which is, for example, in this case, black. So I find the black ones, black neighborhoods in this area, the ones that have a few pixels that have low values. So this function does that for me. And on this image, what you can do is you can run edge detection to create an edge map. So this is edge detection. You remember, right? This is towards x and y axis, and I have the square roots added. So I have the edge map of this image, and I have these markers, And then I use the IM impose min, E and B, so it adds those edge map on top of this marker image, and then I do the watershed on this one. And it just generates regions for me. So it is detecting different regions in that image. It says this is one region. They are connected. This is another region. This is another region. So it is segmenting those areas for me using the map, the edge map, and those binary regions, the IM regional mean. So it's also a very, very interesting way. You can call it marker control watershed. You can manually select these. You can open your images and manually seed it. Say these are my tumor, these are non-tumor areas, and feed it as a mask to your model. We will see that. There is another famous way called active contour. In this one, you have a contour, you start it initially, you give it an initial value, and then it starts growing. So it has some energy terms, it tries to minimize and maximize. But what generally is, in this case, is they are based on energy minimization using partial differential equations. So the contour continually updates until it reaches some minimum of an energy. So let's talk about an explicit contour representation, also known as a snake. In this one, I start with something like this, or better say this, and then I have a map. So all of these points are connected. The first one and the last one are connected, so I have a closed circle. And then for each of these values, I start growing this. So models the contour as a collection of connected points, as a contour C, which is a collection of connected points VI. So this is the energy. So we have an internal energy and an external energy. Inside the bounding area that I have and outside it. So generally the idea is I'm trying to add areas inside that look similar and not add the areas from outside that don't look similar. So I keep growing, going towards areas that have similar intensity in value. So we define an energy based on internal and external terms. The internal term seeks to keep the curve regular and smooth. The external term seeks to match the contour's shape to the image data. So the total energy is energy internal and external added. And this is the way you can present it. Don't worry about equations, they won't be on your exam, but it's very simple to understand. So for stretching, you have dv over ds squared plus beta alpha plus beta dv d square v d square s squared. So these are the terms, the way they are defined, and the final energy, the external energy, is the one that is an edge map. So it tries to find the edges and not go over them. So you start from somewhere, it's detecting the edges in that image as well and tries not to exceed the edges, because those edges are probably the border between your item, your segmentation, and an external item, which is beyond those edges. So this will attract the contour to nearby edges. So the equation is very simple. And once you add these two energies, you have a term like this. So you are trying to optimize this. I'm sure you're familiar with gradient descent. So one way to optimize this equation is using gradient descent. So you have an energy function, which these terms are very simple. And you take the gradient, or nabla E, and you're trying to minimize it. So what you do is you calculate the gradient and update the point in the negative gradient direction. So the new point that you find a gradient at that point and update the point towards the negative of the gradient descent. This is what you do in machine learning as well. These are the derivations, how you can calculate these, but don't worry, you don't need to memorize anything. And in MATLAB, it is, and we will get there, it's just one line. So there are issues, as always with gradient descent methods. They usually get stuck in local minima. So this is one of the issues we have. And they can have self-intersect, and they are a bit difficult to model topological changes. Another way to approach this is level set methods. In this one, the active contour is represented implicitly as a zero level set of a distance function, which is negative inside the contour and positive outside. So here the contour that you have is something like this. You say whatever is inside is negative and whatever is outside is positive, and anywhere that is zero is on the curve. So this one is easier to deal with topological changes. And this is the Chanvi's implementation. It's a popular level set method. So this is the way it works. These are the equations. The energy for this one is defined using these equations, where mu I, mu O are the mean intensities inside and outside the contour. So what it does in this one, it starts with an active, it starts with a contour and tries to minimize the intensity differences inside and outside both. So in this case, the energy is higher than zero because there are variations inside. In this case, there is no variation outside, but there are variations inside. So it is not a pass. In this case, there is no variation inside, but there are variations outside. So we have zeros and ones, for example. And in this one again, there is variations both inside and outside. But if I have a contour like this, there is no variation inside, there is no variation outside. So all of the values, the sum of the I minus a square minus mean in that area is zero in both inside and outside. So in MATLAB, you can call the function called active contour, and it does it for you. So you can give it different parameters. Active contour I, mask, N, Chanvi's, for example, or there are like edge, different models you can try. And what you need to do is you need to give it a mask, an initial segmentation, so that it tries to minimize according to that. So in this example, what I do is I have an image, and I say this green box is my initial mask. How do I do that? I say mask equals false size I. What this line does is it creates an image size input image, makes everything zero, and for 20 to 220, for 150 to 430, make it true. So it's a logical image, like it's binary, 0, 1. So everything is 0, this area is 1. So I created a mask that is 0 size of the image, and 1 in this particular region. So I pass these boundaries mask color G. Just show it. And then I run B equals active contour, I mask Chanvi's. And N is the number of iterations of energy minimization. You can do it whatever number you like. How many iterations should it update? And then you show that. So this is detecting this object inside this mask area for me. This is a better example. So I give it some coins. I read the coins image. And I say, I have 7 iterations, run active contour with Chanvi's model. And what it does, it's trying to find contours that have minimal differences inside and outside the contour. So this way I can find the coins in this background. And now I can count them, right? So I found them, found the active contours around each of them. So now it's just a binarization, and like the bird counting example we had, I just need to find the threshold and say if the value is over something or under something, then doing some cleaning, open, close, I am open, I am close, see what I need, clean it, and then BW label. Find labels for that. All right? So now I can count coins. The way it works is based on energy, inside and outside the counters, and it's a repetitive thing. As you can see, it starts with one big area, which I am giving it, and then it keeps going smaller and smaller. So there are other ways for, in fact, segmentation. One of them is geodesic active counter. In this one, you can use edges. So the previous one didn't use any edge information. It was only based on the intensity values for energy calculation, inside and outside. But this one, if you give the parameter edge to it, instead of Chan-Viz model, it goes from your bounding box until it locks onto edges that are detected. So it looks at the edges that are in that area and doesn't go any further, any more beyond those edges. So the other way is interactive segmentation. There are some ways that you can initially do some initial segmentation on the training images and say this is like the blue line is the background and the red ones is the foreground, and then your model uses this information and then uses the active contouring, updating and energy detection based on the initial values that you have given it, and then it detects this whole object as one object. Instead of stopping here, for example, you could stop here, you say this is a border and you won't go any further, but because you have that as your training input, then it doesn't stop here. There is a video here, you can, if you're interested in this, it's like I think about 20 minutes or 1 hour. It's about image segmentation, and it gives you more details. I don't want to go, as I said, we try to go a bit shallow but broad. So if you want more in-depth information on how exactly these active contour models are working, how exactly those energies are calculated, there are videos you can just watch. The other way that I'm going to very briefly talk about is Markov random field. In this one you have a unary and a pairwise term. The unary term is the cost of assigning a label to a pixel independent of the neighbors. So here you define some cost functions in Markov chain models, in Markov random field models. And you have a pairwise term, which is the cost of assigning a label to a pixel based on a neighbor in the neighborhood. So if we look at an equation, an image like this, so you have a source and you have a sink. This is your background and this is your foreground. So for each pixel to assign it to a sink or to a source, you have to say what is the cost to split nodes, which is there are costs here on these edges. You cannot just simply crop one area from one field to another. There are costs that you calculate. There is a cost to assign to 0 and a cost to assign to 1. And then you try to minimize the cost. Again, we are not going to go into detail, but there is a video on this on YouTube if you're interested, and you can watch for about an hour of your evening. Here we have, in MATLAB, we have a toolbox image segmenter. So if you go to MATLAB, there are some apps that you can open, and you can use those apps for different purposes. Let me quickly open my MATLAB. Okay. So in MATLAB, you have a tab here called Apps. If you open Apps, there are several apps which This is a new installation, that's why it takes a bit longer. I just upgraded it. So there are some apps here that you can use. For example, if you open it, you have ground truth labeler. What you can do with that is you have an image and you want to create some annotations for it. You want to teach your model later, so you want some ground truth information. You have dogs, you have cats, and you want to annotate those images, right? So you can get those images, draw bounding boxes around your images and say this is a dog, and drawing box, this is a cat, drawing boxes, and so on. There are a lot of interesting apps here that you can use. Image acquisition, image labeler, ground truth labeler, image segmenter, image viewer, map viewer, so video viewer, video labeler. So these are the things that you will see. But why do we need to label images? We will get to that. But this is also a link on MATLAB for segmenting images using graph cut models. I ran one image labeler, image segmenter on my image, and I achieved this result. So it's segmenting my skin and my thigh as one group. There are other ways for segmenting an image. One of them is called superpixels. In superpixels, what you do is, instead of dealing with individual pixels, you take a group of pixels in a neighborhood and deal with them individually. So if I have 200 pixels that are all white in an area, it could be just one superpixel, and then I can deal with that as one value. And it saves me some time. So one of the methods that is using this is the SLIC. There are implementations and stuff available. They convert pixels into 5D space, which is LAB colors, and XY position. So LAB color is again another color space that we discussed, and is similar to the opposing theory for the human eye. And you can define K regularly spaced cluster centers and move them to the locations where the edge response is the smallest. So now I want to evaluate my segmentation. I have a few different methods. I have run whatever method I like, hysteresis, thresholding, whatever model I have used, active contours, and so on. And I want to see which one is best. What I need is some ground truth. Is someone who has actually done that segmentation before. Like, for example, in medical images, we hire doctors or specialists in annotations, and they sit behind an iPad, for example, with a pencil, and they draw images, like they want to find vessels, for example. They want to find tumors in images. So they sit and they annotate. They say, this is a vessel, this is a tumor, this is whatever, right? So what they do, they have different classes, and they segment this. So now we have a ground truth, right? The next step is, if I have my model, I have the ground truth, so I want to see how I performed. The next step here is to provide an evaluation, something that once you want to publish a paper, you have to show how good your model is. So what we need to do here is we have to use our results, compare it to the ground truth. We will calculate 4 different values for segmentation. One is true positive. My model has said this is a skin, this pixel is a skin. The ground truth also says this is a skin. So bingo, I have a true positive. There is true negative. My model says this is not a skin. The ground truth also says this is not a skin. So this is another good result. So that is called a true negative. I have false positive. It wasn't a skin, and I said it is a skin. And I have false negative. It was a skin, and I said it's not a skin. Right? So once I calculate these 4 values, true positive, true negative, false positive, and false negative, then I can calculate my model's accuracy. What is the accuracy? It's the sum of true positive plus true negative over all existing pixels. So for one image, I have 600 by 500 by 3. I have said, let's say, out of these 300,000, 200,000 times I have true positive, which means I have detected 200,000 pixels correctly. And then I have 50,000 true negative, which means 50,000 of the negative ones, which were not a skin, I was correct. So what is my accuracy? So I had 300,000 true positive plus true negative, 250,000 over 300,000. So it's something like that, 78%-ish accuracy. So this is the way we compare. And then I have 1,000 images. On each of them I have this calculation, and I say this model, Chai et al., is 85% accurate on data set blah blah, and that other model is 79% accurate on data set blah blah. So this model is better than that model. This is the way you normally publish. But in segmentation, accuracy enough is not a good criteria, because most of the images that you deal with have a lot of black pixels and a few white pixels. For example, imagine you are detecting tumors. So in one huge image, you have like 50 pixels that is tumor and the rest is not. So if you just randomly go and say everything is not a tumor, you're already 95% accurate. Right? So that parameter alone is not enough. You need to have sensitivity as well. So this one is how many positives you have correctly detected. And you have a specificity, which is how many negatives you have truly detected. And then you calculate some other measurements like Dice score, Jacquard score. These are different things that you can calculate, and they're all relationships between these values, between sensitivity, specificity, and accuracy. So this is, again, another example on the previous method. So we read the face, and then we read the ground truths. Once you want to compare your models, there are usually data sets available online, which they provide ground truths for you. So if it is a classification task, you see 100 different classes, which each of them has a folder. In your case, you have like 70 students in this class for that coursework. You have 70 folders, 80 folders, whatever the number is. So you have each folder's label is the label that you need to find. So that is your label. When it comes to segmentation, you need for each individual image, you need a mapping. So the image you have, the whole image looks like some vessels, for example, and then you need a mapping which all the vessels are shown on that image. So what you do is you load your image, you load your ground truths, you run your method, whatever it is. For example, in this case, we are doing the Jalali et al. For skin detection. You detect your results, you calculate your results and say, the true positive is the ones that was a skin and I detected as a skin. True negative is the ones that was not a skin and I said it's not a skin, and so on. And then you calculate the accuracy, sensitivity, and a specificity. And then you can show your results. So in this model, I get 89% accuracy, 99% sensitivity, and 82% specificity. So what this means, it shows me how many are correctly classified, but a specificity is lower due to false positives. And roughly, overall, I have 90% accuracy. The other way is the receiver operating characteristic curve, which there is more detail about it, what it is. But this is based on different thresholds, different parameters. You can draw a curve and show which parameters had which effect. And then you can compare different models on this. And the ones with the higher area on the curve have a different performance. So you can use this ROC curve as well. and based on sensitivity and 1 minus specificity, for example. The way we do it in basically image classification is you will create a confusion matrix. So you have 80 classes. In your case, you have 80 classes of students, right? And you have the actual label and you have the predicted label. So you do know I am, for example, number 1. You have 10 images of me, and you have run your model on my images. In 6 of those images, your model has detected me as 1. In 4 of those, has detected me as 8, 75, 63, and so on. So what is the number that you put here is, for my case, it's like 60%. Right? 6 out of 10, you have detected me correctly. And the ideal confusion matrix is a diagonal one. Everyone is classified correctly, but you won't see that usually. So in this coursework, you are not expected to come up with an ideal confusion matrix. You just need to explain what you're doing, what your challenges are. So next week, we will talk about more image classification. You will get more ideas about how to use images for classification and learn a bit more about feature extraction methods like hog, like blobs, gabo, bag of features. There will be an introduction on machine learning for those few of you who do not know what exactly it is, and I will cover supervised learning. So in half a lecture, about less than a lecture, you will learn supervised learning. I know most of you know it, but it's a good idea to refresh your ideas about it. And it's very simple. It's just you don't need much time about it. Just half a lecture is enough for supervised learning. The week after that, again, half of the lecture we will talk about more feature extraction, and half of the lecture we will cover unsupervised learning. And the week after that, we will go into deep learning. So we will have some ideas about different image classification. And then lectures 8, 9, and 10, we will have a guest lecturer, Greg, who will be talking about stereo vision, 3D vision, and more deep learning. So this is the outline of the next few lectures. There were some questions that, let me see. Okay, are there any questions? Anyone has any questions for me? There were some questions that I wanted to answer, but I forgot what they were, but I will later talk about them. Any questions? Did you understand what image segmentation is? Yes? Yes. Oh, this is segmentation. You are doing classification. So ground truth for segmentation is individual pixels have a label. But for classification, the whole group, like I am label 1. So in any image that you have of me, I am label 1. You don't need individual pixel values. There are two different things.
Well, the OCI part, also, is that sort of like an additional part on the end? Because if we were to train an OCI reader on the images we have, wouldn't we just end up overfitting to that particular style of image, or is that what you want?
It's up to you. If you have the time and you want to train it on a separate data set online, whatever, like MNIST, for example, or more advanced ones, feel free to do that. If you don't have that much time, you can just use the existing ones. All I want from you is I will give you one image, probably my image, and I will want you to find the number that I'm holding and say what number it is. And in a separate function, I will give you my image, and you will find my face and say this is person 1. So this is one part of your work. Similarly, you will be given a group photo, like one of the ones that we took together. You will see that image, extract faces, and say, put IDs around them. This is face 5, this is face 1, this is face 6, this is face 7. How do you do that? You create a data set from your images. These are the things that we have so far covered. So how do you use those videos? The reason you have those videos is because you can extract frames from those videos and add more training images. So your network gets more realistic, gets less overtrained. It can detect more variances, right? So the more training images you have, the better. So what you need to do is you need to create 80 folders, whatever the number of images that you have is. Create those folders, put all my images in folder 1, second person images in folder 2, third image in folder 3, and so on, based on the numbers that we are holding. If we have some numbers missing, we have number 27 missing, don't create a folder number 27, right? You don't have to have numeric numbers. Based on the ID of the person that you see, create a folder, put all the images manually there. You don't have to do that bit automatic. It would be a bit more challenging to do that. You can do that automatic as well. You can run optical character recognition, find those numbers, and then put the whole image in that folder, but you don't have to. You can do this bit manually. So what you do, you have like my images, let's say 10 of my images in folder 1. Now you have 10 videos of me. If you think that 10 images of me is enough, just throw away the videos. But if you think you have more images of me, your network will be better, then you can just write a very, very small script in MATLAB, which is you load a video, you extract frames, and you save them. And then instead of 10 frames from me, 10 images from me, you will have 10 videos, each 3 seconds, 25 frames per second, another 750 images. So then you can have more training images. You don't have to use all of them. You can take 5, 10, 20, whichever number you think you may need. So you have folders of everyone with as many images inside as possible. The big question is, I have your individual photos. You look like this, you have a number. And then I have the group photos. You look like a tiny corner, like a small bit. Should I include that in my data set or not? That's a question for you. So I answer the easy ones. So you can manually crop those and add it to your data set if you want to, or you can eliminate it. But think, your code will be tested on both individual and group photos. So your code not only needs to detect me if I am holding the number, it also needs to detect me if I am sitting there among you. So your code has to have this capability to detect my face in both.
So if you're dividing up the group images, do you have to then look at, like, because we're not holding numbers in those images, so we have to look at them and say, oh, I remember that person was person 23 and put them in that folder?
Yes.
Okay.
That's a... Yeah. And one more thing, that before I answer those two questions. Again, you don't have to put my whole image in that folder. You can only crop my face. Or you can put all those images in one big folder, detect faces, and then put them in those folders. You don't need that number for face detection. You only need faces. So what I'm trying to... The reason I have given you this coursework is for you to get some realistic problem, to deal with real challenges. I could just download the faces, detect faces online data set and give it to you and say, okay, go play with it. But the reason I am giving this is because once you're going to work somewhere, you will see these challenges in data collection. One of you had the problem of converting the format. Some of them were in different format, which is not readable by Windows normally, and MATLAB doesn't read that. So you have to convert those images from HEIC to JPG, for example. Easiest way, yeah, go online and upload them and change the format. Well, are you sure? I went to a website, HEIC to JPG, and it says by submitting your images, you accept our terms and conditions. Okay, let's see your terms and conditions, which we don't usually do. But once you do that, it says all the photos you upload, we can store and use them whenever we want. So can you do that? No. You don't have the right to upload those photos. They will be used. So most of the time, like most of these companies, they have these terms and conditions, and you couldn't just upload your photos. Because they are a service. They have devoted all the amount of money for the payments of the server and stuff because they want photos. They're collecting a data set. They need it for different tasks, so they want photos that they have copyright to. So they set up a website. Yeah, I can do it for you, free. Immediately convert your images, resize your images, and then I keep those photos. I have the rights to that. They are not going to kill you with that data, but this is something that they can use that data for training their models. But you do not do that because you do not have the right. So think about all the aspects, and always, especially nowadays with GDPR, make sure that you are following data protection, copyright issues. These photos are for you. All of you have agreed to have it, and only for you. So do not upload them anywhere that you do not, you know that they are going to keep it. So you will see different challenges. I'm not going to scare you, saying like now every online company is after your identity. But what they are going to do is they use that data for training. So like for archive purposes. You don't want that. So use those images. Do whatever conversion you want. Make sure you are not breaking any laws. You do not need to hold the whole image. You just need to crop the faces bit. You do not need to hold the whole image in your folders. What I would do, maybe, would be to crop the faces and store them so that I am only looking for faces. And then what else I would do is I would consider, I'm not solving it for you, but I would consider that in a big image, my face is, let's say, 600 by 700 pixels. But in a group image, my face is 50 by 50 pixels. You should come up with a logic how to deal with that. And once the test image is given to you, the test images are exactly the same as the ones you have. Just you haven't seen it, you don't have it. I took 10 group photos here, I gave you 9, I kept 1. It's almost identical to what you have, but maybe a slight different angle, maybe some other differences. The individual photos are also the same. They are just randomly selected from different people. So your code doesn't know if I show it an individual photo or a group photo. It has to detect it itself. And it has to find the exact ratio of the face. It has to find the face. For face detection, I showed you one simple solution, 3 lines in MATLAB and done. But you can do more advanced stuff. You can do more online research, see what people are doing for face recognition, for face detection, use deep learning if you like, use different methods, and you will get there. So there were 2 questions there, right? Yeah? Yeah, answer.
Yeah, which formats do we have to expect? That we need to expect videos and photos, right?
Yes.
And which formats? Like JPEG is standard, or?
I won't give the I won't give the high for the test. I will make it JPG and MPG. Something that MATLAB reads. So also Python reads. Any more questions?
What about the live pictures we converted into video? So what do we do with that?
So for the live pictures, they are basically the videos that I'm talking about. So they have an image and they have a video, which is a couple of seconds before and after that. So you can extract frames from them and add more training images, or you can just ignore them. See which one your model needs more. I think if you have more images, at least 10, 20 from each video is a better idea. But if your images are too blurry, if you're going to have like all those random changes in position and there is blurriness in them, they might even reduce your accuracy. So you have to choose some, I would, but you don't have to. Okay, no more questions? All right, so see you in the lab and also next week.